The 12th in this series on simultaneous equations is going to introduce the concept of row operations. Previous videos then demonstrated that if linear simultaneous equations can be represented in a row echelon form, they can be solved very efficiently. This video shows how an original set of equations represented in matrix form as Ax equals b can be modified with the aim of creating a row echelon form. The focus of this specific video is on understanding how row operations are equivalent to matrix multiplications. Some concepts then. We want to solve Ax equals b by using matrix multiplications on the left. That's key, on the left. So you'll see here we've pre-multiplied by the matrix D on both sides. And these two expressions are equivalent as long as D is square and full rank. We could also pre-multiply by a number of matrices. So you see here I've pre-multiplied on the left by F, E and D. And again, solving Ax equals b is exactly equivalent to solving FED Ax equals FED b, as long as F, E and D are square and full rank matrices. So what is it we want to do? What's the key concept we're focusing on here? We want to ask, can we find a sequence of matrix multipliers? So you can see I've used ... to say there might be many, and then FED, so that when we multiply these all by A, we get the identity. Because if we do this, then the same matrices multiplied by B will give me X. So whatever operations I've done on A will end up giving me X. So let's continue with these concepts. So what we've said is solving Ax equals b is equivalent to solving FED Ax equals FED b as long as FED are full rank. Now, what we want to do is find a sequence of multipliers such that when we multiply by A, we get I, because that implies that the same sequence of multipliers onto matrix or vector B gives me X. So the key thing is the same operations. The same operations I've used on A can be used to solve for X. And also, if you happen to need it, you would also see that the product of all these matrices would give you the matrix inverse. Now, what we want to do next is show that this pre-multiplication, so pre-multiplication on the left, is actually equivalent to row operations. So let's consider this matrix here D, which you can see has got a 1 in the top row, a minus 1, 1 in the second row, and a 2, 0, 1 in the third row. And if I was to look at the matrix DA, what you would find is the first row of DA is the same as the first row of A, because the first row of DA is given by this top row, which you see just picks up the first row of A. The second row of DA is going to be the second row of A minus the first row of A. So you can see we've got here, it picks up the second row with this plus 1 and subtracts the first row with this minus 1. So you can see pre-multiplying has given me a row operation. Okay, and finally, if we look at the third row of D, we can see it takes twice the first row of A and adds to it the third row of A. So again, we've got a row operation. So what you see is pre-multiplying on the left by D has given me row operations on A. And remind ourselves that our objective was to look for row operations to find a sequence of matrices D, E and F such that we can essentially find the matrix inverse. But the key thing is that these matrices can be represented as row operations or vice versa. So by defining a row operation, such as this one here, in essence, I'm defining the matrix D. So in summary, pre-multiplication by a matrix, and I should put here, this is on the left, but I have used the word pre-multiplication, is equivalent to doing row operations such as adding and subtracting multiples of some rows to others, and that's the key statement. So if you can think of a row operation, you can think of an equivalent left multiplier. With sufficient and appropriate matrix pre-multipliers, or equivalently row operations, you can solve for x. So that's what we're going to try and do. And the key point is the analogy with the solution of linear simultaneous equations, where row operations are used to eliminate variables. And in essence, we're going to represent these row operations as matrix multipliers. Now, some basics, just to remind yourself. An augmented matrix is transformed into a row equivalent matrix if any of the following row operations are performed. So we can swap rows. We can multiply a row by a non-zero constant, or we can add a multiple of one row to another row. And the key point here is where we use this arrow, in essence we're saying replace. So we're saying replace a particular row with a multiple of that row, or a multiple of one row plus a multiple of another row, and so on. Let's give an illustration then. Here we've got two linear simultaneous equations, and we're going to do a row operation to solve. So we're going to add a row 1 to row 2 to eliminate x. And you're used to that. That's relatively standard. Now let's look at the same equations in matrix form. And again, we can do exactly the same operation. So you see here we said add row 1 to row 2, but what I'm going to do instead is I'm going to say that's equivalent to pre-multiplication, so that row 1 is unchanged. You can see the top equation is unchanged, so we want the top equation to be the same. So row 1 is unchanged, and row 2 becomes row 1 plus row 2, and you see that's equivalent to this operation here, add row 1 to row 2. So in order to do that, we come up with this pre-multiplier D. You can see the 1 in the top row says row 1 is unchanged, and the 1, 1 in the second row says add row 1 to row 2. And you'll notice I've done the same pre-multiplier here, multiplying my B. Now if I multiply that out, this is what you get. Okay, you see I've now got my triangular or row echelon form, which is what I wanted. So the pre-multiplier matrix D has created a row echelon form. Now let's do a slightly harder illustration. So here I've now got three variables, and you'll notice I've given these labels R1, R2, R3, so we can keep track of what rows we're talking about. So if we solve it in the classic method, I can say row 2 goes to row 1 plus row 2, row 3 goes to 4 row 1 plus row 3, and that gives me these two expressions here. And then I can say that row 3 goes to 2 row 2 minus row 3, and that gives me this expression here. So there's your standard method on pen and paper, and you can solve. Now next let's look at this in matrix form. So you can see row 1's up here, row 2's here, and row 3 is here. So can I represent these row operations with an equivalent pre-multiplier? So in essence I've said I want row 1 to be unchanged, row 2 goes to row 1 plus row 2, and row 3 goes to 4 row 1 plus row 3. So the pre-multiplier that does this is this D. You can see the top row, row 1's unchanged, the second row becomes row 1 plus row 2, the third row becomes 4 row 1 plus row 3. Now I'm looking for an operation that says row 3 becomes 2 row 2 minus row 3, and row 1 and row 2 are unchanged. So this is the E that will do it. You can see row 1 unchanged, row 2 unchanged, row 3 is 2 row 2 minus row 3. So now you can see if I write D, E, and multiply these onto A, what has it done? It's created my triangular form. And then I can update the right hand side by doing E times D on the original B, and that gives me my updated right hand side. But the key thing is for you to see that these matrix pre-multipliers are in essence equivalent to row operations. And if we can choose suitable E and D, we can create a row echelon form, which is then easy to solve. So in summary, pre-multiplication by a matrix is equivalent to doing row operations such as adding and subtracting multiples of some rows to others. With sufficient and appropriate matrix pre-multipliers, you can solve for x by reducing A to row echelon form. Now, we've not told you how to define these systematically yet, so that will come in the next video. Key thing to remember is that row operations are efficient compared to determinant and matrix inverse operations deployed in the resources 8 to 11. So the efficient solvers you'll find in computing tend to use row operations.